Yeah, hi, I'm Veronika again. So we usually develop systems that are flexible and then can quickly adapt to the new conditions, so they can be effective and competitive and allow our products to stay on the market. And today I'd like to tell you about the solution that we use in Appadil in order to manage these changing conditions and to control our system behavior based on them. So a few words about me. I'm Veronika. I work as a Scala team leader now at Appadil in BitMachine product. You can scan this QR code later if you want to contact me for any reason. Don't worry about Scala today, though it's my main language, but I really tried to focus on the software design in my talk. And I will mention functional programming stuff, but it's like higher order functions, pattern matching, and functors. I hope that most of you are familiar with this through different functional languages. Before I define the problem, I'd like to start with an example. So let's assume that you work in a big product company and you have like a huge amount of users, like millions of them, and your manager comes to you and say like, we have Black Friday season soon in the USA, and we want to show the discount prices for our USA users, but for all other users, we want to just show the standard regular price. Probably you will write something very simple, like just if-else, and show this discount price for specific users. But then you may remember that actually you want to test this code first only on specific SDK versions of your application. And though your condition becomes a little more complex, it's still okay, it's still manageable, but not so good anymore. But then these conditions like keep growing and growing. Your managers, your, I don't know, salespeople, they imagine new scenarios for this feature. And every time they need to wait when you actually implement this in your code and deploy the application, test it. So it takes a lot of time for developer and for the non-technical users as well. So we have two problems here, like messy code with a lot of different conditions here, and the problem that non-technical users, like our managers, they can't write the code, which is probably for the best. So we can try to write it in a better code style, because this huge if-else is not going to work. But this is the example from our application. Like, we extracted it to fancy variables and make our if a little bit more clear, but it still doesn't solve the problem with non-technical users. And if we have a lot of places in our code where we need to call these conditions, they kind of take the place in our app, and they do not make much sense for us. So from here, I'd like to define the problem itself. We need to manage changing system behavior in real time in a manager-friendly way. And I will break it part by part, so it will be more clear. So first thing, we need to actually manage changing behavior of our application, which means that we have some situations in our code where we need to check some condition and actually choose the path inside our application where we want to go. We want to make it in real time. We don't want to just change the code every time these conditions change, so it should be somehow possible to make in real time without redeploying or something like this. And it should be manager-friendly, so non-technical users can actually just open some editor, write some normal text, and expect that it would somehow translate into the program itself and do some stuff. So from this problem, we come to the requirements for our solution, actually. I will call it rule matcher, and it should verify that rules are valid in terms of technical perspective and business perspective. It should keep rules easy to read and manage so that different users would be able to understand them. And it should be quite abstract. It shouldn't be connected with some specific domain, so it should use any application attribute. What do I mean by attribute? It's actually value of any property inside your system. So it can be something connected with user, like his ID or his phone number, country, device settings, or something like this. It can be some system information, like current date, for example. And it can be anything historical that you already have in your database, like amount of orders of this user, or his last activity time, or prices of some items, like anything. And I wanted to emphasize here that developers are still responsible for defining these attributes, because only they can actually substitute values of them inside your application, inside the code. So managers can only ask for the developer to add more attributes, but it's still on the developer's shoulders to write this. So if we remember our example, we have some user, and we show $20 price for this user, and we know his attributes, like the requests coming from this user phone, they're from US, and he uses iPhone. And we have some other users that may probably be from other countries and using different operational systems. And we have our rule matcher, where our manager can just type, like, for users from US using iPhones, please show the discount. And after evaluating these rules, for every user, we will show the discount price for this cute cat and tiger, and for the dog, sorry for him, it will be still $20 price. So in terms of our global goal for today, we want to go from the first approach where we have conditions and logic connected like inside one application. We will separate these two concepts, and we will leave all the conditions, all the rules for the users, and inside our application, we will just match these rules, and if they are true, do some logic, and if not, do something else. That's the main idea of the solution for today. So this was the business description, and now I will go into the implementation itself. I will start with an architecture, domain models, and end up with the recursion and recursion schemes in the end. So this is brief architecture, and there are two main parts. The first part is responsible for transforming the input of the user into some valid domain model that we can use later. And there are two models here. It's a parser and a validator. So parser will just transform our input into domain model, and validator will use information about attributes and these rules that we get from parser step and validate them and return us valid rules that we can use later. And we will have matcher part, which will take these valid rules and actual values of the attributes from the real application, evaluate them, and return us result, if they are true or false, basically. So the first two parts, they are kind of simple to implement, so I will just cover it very briefly, and the matcher is the main part, and I will spend more time on explaining this. So as I said before, parser should be just a function or a module that will transform our string into the domain model. And for our case, we choose this notation for the rules, for the conditions, and it's attribute operation value. So we can write different expressions, like something greater than something or equal to something, and anything. And in our domain model, it's basically the same. It's also attribute operation and value. So you can choose any syntax that you want, because basically you just need the code that will transform one into another one, but we decided to use this one. So just briefly, operations can be simple enums, values can be typed, so if we decided to use strings, booleans, numeric values, arrays, and the rule will be just attribute operation value, as I said before. And for parsing, you can choose anything. You can use regular expressions. We choose fast parse library. It's kind of cool, but actually it doesn't matter any way that you imagine you can use this. Then we go into validator. So we have our list of rules, and we know our attributes, like country, device, operational system, etc. And we need to check if this rule makes sense, because we can't write, for example, that country is greater than something, because it doesn't make sense. So we decided to validate two things here: operations and values for the attributes. So if I talk about values, we know for sure that for some attributes there are only limited amount of values. Like country, only specific values are allowed, and we can actually write them, save them, and validate if the value that is used in the rule is one of these values. So it's pretty simple. And for operations, we actually need two things. We need attribute on the left side, we need the type of this attribute, and we need the type of the rule value on the right side. And we know the operation. So we can just define for this pair of things what operations are allowed. So for example, for this type of rule, we know that country is a string attribute, and we know that US is a string value. So in our system, we allow only equality operators here. And in this case, this rule has equal operator, so it's OK, and we return that it's a valid rule. But if, for example, we had a greater operation here, then it's not valid, and we just don't allow our users to input these values. Yeah, always forgot about this. So after these two steps, they should be actually combined, because you can't save, it's not logical to save rules that are not valid and validate them later, so it's better to parse them, validate them, and return to the user like, is it okay or not? So we find the solution how to transform this input into some domain model and save them to use later. And so here goes the mature part. Like we have our rules, we have the values from the real application, but how do we know that these values correspond to these rules? We need some solution to return to us this result. Like, is it true? These expressions, are they true or they are false, or maybe there is some error here? So as our mature, as you can see, it's taken as an input a function from attribute to value, which means that we can use any structure before and just pass the function inside this mature. So we can use maps, we can use lists, we can use anything, but we just need to return this function from attribute to value. So in our case, we usually create a map and just map these real values from request or from system. Just define it in your code and it works. The next thing that we need to somehow evaluate rules. So we need this concept that we called predicate, which is basically a function from the real value to the match result. But with this in mind, we can only define, it will return either error or Boolean value. But with this in mind, we can define only very simple predicates, like true predicate that will be always true, or false predicate. But we need more complex predicates for the rules. We need to compare things with themselves. So we will create a rule predicate. And I will use this notation later. So just if we imagine this rule predicate and it has a toString method, it will be that something, then operation and value. So in this case, it's something equals US. Some actual value equals US. And we can define any amount of these rule predicates, like just define apply method for them, because it's simply just an expression with the left side and right side and operation between them. So we should just check that types are correct, that numbers are compared with numbers, strings with strings, etc. And it's very simple logic, just perform these actual operations. So now for any rule, we can create specific representation of the predicate that we will apply to the value and get the result. But when I talked about the rules, for example, if we have these three rules one by one, in our system it means that it's AND, they're all combined. So we need that all of these rules are true. And we can actually define just a list of predicates to evaluate them. But what if we want an OR operator? What if we want to make more complex rules? And we can make nested rules, they can be checked one by one in more complex scenarios. We use indentation for this, like in Python. Not sure that our users are happy with this, but yeah. So in this case, we actually choose one of the branches. If the value was Android, we go with the one branch, and if it's iOS, it's another branch. But with this in mind, we need to somehow represent these nested structures. So we added children attribute into our rule object. So now we can like put these nested rules into the children property, and they will be like combined together. But now we can't represent it as a list of predicates because we need to actually choose one of these rules and go deeper. So to solve this, we need recursion, and we need trees, actually. So the flow will be like this. Like we will build a predicate tree from the list of rules. Then we will recursively evaluate all the predicates for the specific values of attributes. And then we will collapse it to our final result. So we will like go through the tree, and if we reach the end, it means that we have the result. Or we can stop at some point and return false if we can't find the predicate. So we will start with a simple recursive tree. It will have a leaf, which is basically the end of the tree, and it will have the result, like true or false. And we will have a node that will be like containing attribute and its children. So it will contain subtrees. And to actually reach the subtree, we need predicates. Like we will evaluate these predicates, which means that we can go deeper into these subtrees. So if we represent our rule, like very simple one, in the shape of a tree, it will be an attribute country. It will be the predicate to actually like go deeper. And if it's true, if this predicate will be true, then we will reach the leaf true. And if not, we will stop. And in the code, it will be something like this. So for our more complex rule with the OR operation, we will have these branches of the tree. So we will choose either two of them and go deeper to evaluate the predicates once again. So actually, we can create very, very big, complex rules with like many, many branches of this tree and just like pass through them. So if we try to build this tree from the list of rules, we will end up with a recursive function because we need to recursively create these subtrees. It's actually like not very important what the code is, but if I will cover it briefly. Like if it's the empty list of rules, then it's our leaf, so it's our terminating case for recursion. If it's just one node, we just create a predicate from this and end with the leaf because we will go recursively and fall back into our first case. And if it's a list of rules, we will just group them by attributes and create these subtrees from these rules. But we will see the recursion here for rule children. Then when we build a tree, we need to somehow get the result from it. So it's basically like a fold function for our tree. And again, it will like match through our tree. If it's a leaf, then it's an end. And if it's a node, there are like two steps. The first step is to find the predicate to actually choose some of the branches of this tree. And if we find the matching predicate, if it's the predicate that returns true, that means that we can continue to the next subtree. And if not, we will just stop. And this second part is about this. So if it's just, if it's not matched, then we return the result. And if it's the subtree, then we call fold once again the subtree and continue. So our final matcher will look somehow like this. So we will build a tree from the values about information about attributes and from the rules itself. And then we will call fold on the actual values, and it will collapse our tree to the final result. We can stop at this, but no. We thought about, like, can we hide this recursion? Can we make it more abstract, more generalized? And actually, yeah, we can. All we need is three things. It's fixed data type, it's higher kinded tree, and it is functor. And recursion schemes, basically. But these are the three things for recursion schemes to work. So fixed point, it looks a bit scary, but usually, like all the libraries that provide you these recursion schemes, they provide this class for you, so you don't need to write it. So it's basically just a point of a function where it's like the function on the specific argument equals to the value of this argument. So for the very simple function of the square, it's 1, for example. And this thing will help us in our tree. So we had this recursive tree. at the start. But then we add type parameter to it. So now it can be tree of strings, or tree of ints, or tree of trees, for example. And we, like, leaf will stay the same, and node will have not trees in the children attribute, but it will have a's there. So if it's tree of trees, then the node will have the subtrees. But if it's tree of ints, then it's just simple tree of ints. And with this fix structure, we can actually make tree of fix of tree. And now there is no recursion, actually, because this second tree is just a type parameter for fix. So it's basically tree of fixes. It's not tree of trees anymore. Because with tree of trees, when we want to represent tree of indefinite depth, we can't write like tree of tree of tree of tree. It's not convenient. So now we can actually just write tree of fix of tree, and this will like capture recursion in here. And we need a functor, which is basically like a map function for our tree that will transform trees of some type into trees of another type. And it's very simple. We just map on our children. If you remember our build function that was recursive, we actually also did this map on children, but now it's like hidden inside the functor instance. So recursion schemes, there are many different implementations. Like I think in many functional languages there are different libraries for this. In Scala, the most popular one is Matryoshka. It's like it provides you this fix type with all these fancy functions that you need, so you don't need to implement them, but I just like showed them there, so you will be like more familiar what it does. So we need actually two things, folds and unfolds. And unfold, it's called anamorphism in this Matryoshka library, in the recursion schemes in general. It's basically a function that knows how to make a functor instance from the type A, and it returns us a function from A to fix of f. So it actually helps us to take a value and like unfold it into recursive structure, into this fixed structure. Also, we need fold, which is called catamorphism, and it's doing the opposite. It's actually like it's the function from this fix, from this whole recursive structure into the one value, so it collapses this value. And there is also a very useful thing that is called hylomorphism, which is the combination of anamorphism and catamorphism. And as you can see, like if we just call first anamorphism and then catamorphism, we will need to store this fix of f somewhere. But this hylomorphism, it actually eliminates this thing. It is just a function from the A to B. So this intermediate fixed structure, it's not needed there. So it's just the function from result to another result. And it's pretty cool. So our new matching flow, we will still build the predicate tree, but now it will be this higher kinded tree. Then we will find a path inside this tree for the specific attributes, and then we will follow the path and collapse it into the result. And now we still have this build function, but there is no recursion here anymore. Like now we just define one step of building the tree from the list of rules. And it's like wrapped into coalgebra, but basically coalgebra is just a function from A to f of A. And our ana function, anamorphism, it takes this coalgebra and returns us a function from the list of rules to this fix of tree. So we can create this recursive tree with a fix of tree. Then we split this fold into two new functions. First one, again, we'll be using coalgebra, and it will be the step of how to get the result from the fix of tree. So it's basically building a path through the tree for our attributes. So to explain this, like we have a tree, and we have a specific values for our attributes. Like we know that OS will be equal Android, and the ZK version will be this one. So we go one by one, and we evaluate the first predicate, we check it, and it's true, because Android is equals Android. And we build a path from this, and we eliminate this tree part. Next, we evaluate next predicate, and we again continue to build the path. And we will end with the leaf here. So now we have all this path through our tree for the attributes. And then with this env function and this built-in path function, we have a path, and then we just use collapse that will collapse this path and give us the result. So from this one structure, we will go to the result. So in the final implementation, with these recursion schemes, we will create a tree using anamorphism and our build function, which is not recursive anymore. We will create a path, again, recursively, but it's not visible for, in our explore function, and collapse the result. And if we simplify it a little bit, we actually get this pretty simple code, I'd say, that we built a tree again, and with this hylomorphism, we unfold and then fold into the result. So it's basically the same that we have before, but in a more generic way. And in our build and explore functions, there is no recursion anymore. So you just look at the clean business code. We use this solution for in different parts of our system because it's quite abstract and it's not domain specific. So you can define different attributes, you can define syntax that you want, and validation that you want. We use this for a feature flag service because it's, I guess, the most obvious example of using these rules. So we have a lot of different features in our application that are controlled by these rules. So our managers, our salespeople, different people from our company, they just try these rules and they see in real time how this affects our application, that it gives some results. So they can quickly check different hypotheses and progress with this feature or just stop it and remove it from our code because it doesn't make sense. We also use this for in different part of our application because we are exchange system between publishers and agencies that sell the advertisement. And we know for sure that some of the agencies will never respond to us with their advertisement because they, for example, do only videos and we have a request for a banner, for example. So we just write the rules when we call these agencies. So we do not do this when it doesn't make sense. So we actually limited load on our service by this because we have a huge amount of incoming requests and even more requests that we send, outcoming requests. Or this can be used to model some complex system behavior if you need. Of course, this solution is not for every use case. I'd say that it's very useful when you have a lot of different conditions and you really need to change them very, very often because this solution is quite scalable. You can create many, many different rules. They will be evaluated quite quickly. And as they are abstract, you just need to implement this once and use them in different parts of your applications, like an SDK, for example. But it's quite complex. It's complex to understand which rule was the cause of some specific behavior inside your application, because when not the developers, but the managers or someone else control the application behavior, it can lead to some weird situations, and it's really hard to understand which rule causes this specific behavior. That's pretty much it. Thank you for your attention.
Thanks, Veronika. Yeah, we have time for questions, so I see one already.
Hi, thank you for the great talk. I was just curious, but then you kind of said at the very end that you don't know what kind of rule caused breaking something. Mm-hmm. So, because it's a standard problem if you have validation or parsing and stuff like this, that in for comprehension you would short circuit and get one, right? And here you go into option, so you get none as a result. Did you consider using eithers? Because one option that I always used for more complex things were either nels, where I could store the list of errors, for example, because to me conceptually it's kind of the same, right?
Yeah, but it's actually either. The mature result, it's either error or Boolean, but I was talking about business errors. Mm-hmm. When the rules are correct, but when you have, I don't know, 100 places in your application where different rules are evaluated, and they all come in once, you don't understand like why one conflicted with another one, and it like lead to some weird behavior. So you need to actually remember which one was controlling something and why it happens. And sometimes it can be complex when there are like hundreds of them.
Okay,
Mostly about this.
But but you have the capability of storing all the errors, kind of if you're parsing the tree.
Yeah.
And you parse the whole tree. It's not like you kind of just, if it fails, like you just stop.
No, actually when we just parse and validate, yeah, we, as far as I remember, yeah, we evaluate all the tree so we can return all the errors to the user, so yeah.
That's really cool. Very last question. Do you have slides for this? Maybe, or code?
Yeah. I mean, they're on this application that's used in Lambda Days, and
Thank you.
I think by this QR code they're also available, but I will check.
Yes, we're gonna go up.
Okay, thanks. Thanks for a great talk, first of all. I have a question. So I feel myself like I'm diving into some language parsing structure, like kind of new language. And when you're explaining how this syntax is parsed and wrapped in the trees, and I wondering maybe it's possible to, on the some step, to just make actual code snippet from it and execute. I know it smells maybe bad, and you think like wait, dynamic code execution, but maybe not so functional. But we can wrap it into I/O or something, and like to avoid these complex tree structures. Can we make it on some step real?
I try to understand your question, sorry. You mean that instead of creating this whole tree?
You know, like input that you got from the manager, it looks like almost like a code, right?
Yeah.
And why it can just look like a code in real? Like
because people like don't know the code. Like
yeah,
they can understand.
But
this
anyway, the manager that works with it, he or she should follow the rules of the language you make. So it's anyway like some kind of DSL. Maybe it's simpler.
DSL, yeah.
It's simpler than just actual Scala code,
yeah.
for sure. But for such cases, when you just construct a list of or a sequence of ifs, or
you mean actually just
similar.
write if else and it
yeah,
is
just
still okay for managers.
At least from the first look, it looks like it just helps to avoid if else keywords, but in general, it's the similar thing to the code.
Yeah, yeah.
Yeah, for sure. I know that we can work around some code injections with validation and whatever. But after that, for example, we validate the rules and we just combine them into code snippet and we dynamically execute it. Can we make it possible? I mean, maybe.
I mean, it's still possible to choose any syntax that you want. So you can replace it with the standard Scala syntax, or you can even make some nice UI for the managers so they can just, take some specific blocks and combine them into the rules. But yeah, and then just like evaluate them by this whole approach that I showed you. I'm not sure that I answered your question, but
okay, maybe we can catch up later and discuss.
yeah, sorry,
Sure.
just hard to follow.
Hi, thanks for that. We actually have a very similar system for similar problems and at Bellroy, and I was wondering what the scaling has been like for you in terms of how the managers and other non-technical staff have enjoyed working with this system, and whether and how quickly the rules have become more and more complicated. Because we've had instances where we've wound up having to start providing essentially like a small standard library of built-in functions to let people say the things they want to say without giant expanding DSL snippets, and it's been really effective, and I think it's cool to see the idea reinvented. So I'm wondering what the scaling story's been like at Appadale.
Yeah, I'd say that as we developed this feature flag service using these rules, that by the help of this feature flag a concept, we have different experiments. So actually these rules inside one experiment, they're pretty small, like maybe 3, 4, 5 lines, maybe 10, but not more than that, because people's brain is not like, it can't understand what is the big structure here. And so I think that with this concept of feature flags, it helped us to actually avoid this problem of very big amount of rules in one place, because without this separation in different experiments, it will be just one big part of the rule with this or, and it will be hard to manage. So yeah, in our case, just feature flags help.
You're not done yet.
Yeah.
So, if I understand correctly, what might happen is that a manager goes into work one day and he writes some new rules, and they get deployed directly. And in a sense there, you have a system running live, which has never been tested. You know, what could possibly go wrong?
Everything.
So, I can imagine you might sell 1 million puppies for €0 or something.
Yeah.
But how do you organize testing of this system as a whole to ensure that that kind of thing doesn't happen?
It's a great question, actually. We just we don't have some system for testing this, but we just really hope that our users, we hope that they start from some very simple rule to just check on very small portion of traffic. We have a real-time analytics connected to our system, so they can quickly check the results, and we have many alerts on the data itself. So when we see that our spend, goes from $100,000 to 0, then we react on this. So we created a lot of safe stuff around our system. So we react on everything, on metrics, on analytics, on data, but this system itself, it's not. We don't have some solution to actually ensure that the user will not do something stupid in terms of business logic. So, yeah.
Thank you for the talk. I didn't know if condition could go so far, but it can. I wanted to know, so for debugging, let's say, you mentioned that at the end of the talk, you compute the whole tree, so you know the path the condition took through the tree, right?
Yeah.
Surely there should be a way to log that or show that or some statistics on that, or do you do any of that, maybe?
Yeah, it's possible, but no, we don't do this. But yeah, but it's possible, for sure, yeah.
You mentioned the tree is not very deep usually, because 10 lines of code, so maybe that's not so useful.
We actually thought about some, trace to see the whole path of different trees, like which trees were evaluated one by another, so we will see the features that actually applied, but we didn't implement it, but we thought about it because it will be really helpful to see the whole trace of this and to debug, because now it's a bit hard.
Thank you.
Okay, I think we have time for one very quick question. Who was left? Okay.
I do have a question about the implementation that you just transferred from the recursion to those anamorphism and hylomorphism, because we do have implemented almost the same thing, a bit more complex, but we do have it with the recursion, and every time I try to debug it, it's impossible. If I have a filter that is like this and/or expression, and I have some set that I applied to, I usually just somehow deconstruct the filter and apply one expression by another, just to see what went wrong. And I imagine that if I use this another abstraction on top of it, it would be just completely even I wouldn't know where to put a breakpoint or anything. So I want to see if there are any benefits or if people in your team are comfortable with such abstraction, because I'm a mathematician and I was kind of mind blown.
Yeah. I mean, I think that the main benefit of the recursion schemes in general is that you can hide this recursion in functors and in this anamorphism, catamorphism stuff. I'd say that in this case specifically, it's not like a big difference from the real recursion implementation. But I think that in some more complex example, like with the decision trees or something like this, it's better because you can actually like create more clear code and just look at specific steps instead of this recursion in your mind, you know. But in terms of debugging, I don't think that these recursion schemes will help you. I think it will even make it worse. So I'd say that this case is maybe not the best fit for the recursion schemes, but it was worth trying, and like now we're kind of happy with it. So just wanted to show the case, and you can expand it to the more complex solutions.
All right, thank you.
All right, thanks. I think there are still some questions around, but you're going to have to catch Veronika.
Yeah, we
after.
can speak later.
Yeah, as before, please leave through the front, through the door on the right to vote on the presentation. Thank you.